My name is Pouran Behnia. I work as GIS specialist with Metal, and I also work with data analytics team on applying data integration models for Metal transects. So the location of study area and geology of Noranda area is shown. We used random forest as the data integration model in this study. Based on the characteristics of VMS deposits in the area, the following regional area criteria were considered as possible vectors to ore in Noranda area. Presence of volcanic rocks, proximity to semi-volcanic tonalite, phalangemite, granodiorite, intrusive bodies, presence of geochemical anomalies for copper, lead, zinc, gold, silver, and other VMS pathfinder elements, presence of chlorite and sericite alteration, and proximity to semi-volcanic faults and shear zones, particularly the faults trending northeast. We also selected airborne magnetic data and 3D geophysical data to examine the potential predictive power of these data in VMS mineralization. Because all data were not available for whole study area, we selected 3 regions for regional interest for integration. The first region, which is shown in red, there is no 3D geophysical data available for most of the northern parts of the area. So we didn't use these data for this model. The second area is the area which we have all data available for it. And the third area is shown with green color. This is the area which is limited by the VMS mineralized bodies. To prepare the lithology map, we reclassified all volcanic units as felsic, intermediate, mafic, and ultramafic volcanics. The same was applied for intrusive rocks. Metamorphic and sedimentary rocks were classified as mountains. TTG, semi-volcanic TTG intrusions were extracted from the geology map. For the bodies larger than 1 square kilometer, proximity zones up to 5 kilometers with the interval of 500 meters was created. And for the small ones, which is shown as green color, we selected proximity zones of 2.5 kilometers. The 2 class proximity maps then were merged to give 1 proximity map. Faults and shear zones were grouped in 4 major and minor northeast and northwest trending faults. For the major faults, the proximity meter of 700 meters with the interval of 50 meters was selected, and for the minor faults, the proximity zones were set to 350 meters. The lithogeochemical data were extracted from CGEM website, and Hemming did the chemical analysis, and the censored and missing data were imputed using Z composition in R, and we see the plots, and then the data was transformed to centered log ratio for closure problem. Indicator elements for VMS mineralization were used based on the VMS model and also availability of data. Then principal component analysis were applied on the selected data. And as we can see in the scree plot, About 90% of the variance is explained by the first 10 components. The PCA biplots also show the PCA values and the loading values of variables in each PC. We can see the relative contribution of the variables. Most of the major elements have a high contribution in the first PC, so PC1 can account for the lithological variations in the area. But copper, lead, zinc, nickel, gold, and silver and sulfur show high contributions in PC2 to PC6. So we selected these 5 pieces to use as geochemical maps in the model. Before using these data, the data were interpolated using inverse distance gating method in ArcGIS. Also, cerussite and chloride indices were calculated using IOCAS software and then were interpolated to create the alteration predictor maps. We also use 3D geophysical data, including density, susceptibility, and resistivity models. Mustafa gave the details on these data. And in this study, we selected grids from their near surface to depth of 6,750 meters with interval of 1 kilometer. So for each property, we had 7 maps included in the model. Total magnetic field reduced to pole and upward 200 and 100 meter upward continuation. First derivative, vertical derivative, and tilt map also were selected. Random forest is an ensemble of individual decision trees. A decision tree is composed of nodes and edges and is used for making decisions. Training data are used to train the classifier rules using bootstrap sampling, which means each tree only uses 2/3 of the training data for classification, and the remaining 1/3, which is called out-of-bag data, is used for validation. Each tree randomly selects a subset of input variables, and the combination of all decision trees gives the majority vote. The final product is a classification map and a probability map for each class, which we use as the prospectivity map. There are 52 VMS mines and deposits available in the area, which we used as training data. We also need some locations as non-VMS as training data. These data were randomly selected 1 kilometer away from the existing VMS mineralized bodies. Usually, the number of non-VMS to VMS is set to 1 so that we can have a balanced training data. Imbalanced data may cause to lower accuracy for the minority class. But because the number of deposits is always less than non-deposits, here we try to use a ratio other than 1. We selected 1.5 to compare the results with the case when the ratio is 1. This was repeated 10 times with using different sets of random points. That means for each data set, we repeated 5 times. Nmap box was used as for classification, and we set the number of features to square root of all features. And Gini coefficient was used as the impurity function. Number of trees were set to 500 to 1,500, depending on the experiment, and the classes is of course 2. Here we can see the probability maps created using two ratios. The high probability areas is shown in purple, and we can see that existing mine and deposits, which are shown as in red, mostly lie on the high probability areas. The two maps are similar, but have some differences in these areas. And this one is the mean of 10 probability maps created from 10 probability. One way to assess the probability map is using area frequency curves, in which the percentage of cumulative frequency of deposits is plotted against the cumulative percent of cumulative area from high probability to low probability. The one which is in red is for ratio 1.5, and the one shown in green is for ratio 1. And we can see that ratio 1.5 shows a little bit better performance because of the area of under curve. About 95% of all deposits lie on the top 7% of high probability areas, and this is about 13% for the map for the ratio of 1. The accuracy can also be assessed using the classification map. When we assess the classification map using the same data which we used as training, we may get high accuracy, which actually is overestimating, as is seen in more than 98%. To avoid this overestimation, we may use k-fold cross-validation, in which all the training data are divided to n-fold, k-folds, and each fold once is used as test data. And the other n-1 groups are used as training data, and the predictions are made for the group. This is repeated for all of the groups, and the predictions are used to calculate the accuracy. We used 10-fold cross-validation for our data, and as we can see, the overall accuracy is now much less. For ratio 1 is a little bit higher than ratio 1.5. But this map classifies the VMS areas up to 10% less to VMS class. And class-wise accuracy also is shown. We can see in the ratio 1, all accuracies for VMS class is higher than the case when the ratio is 1.5, but the accuracy for non-deposits is less than the other set. Finally, we assess the accuracy using test data. There are 15 VMS showings which were not used in the classification. Using this data, we got the overall accuracy of 83 for ratio 1 and 73 for ratio 1.7, which is less. And also we can see the area frequency curves. The success rate of classification is shown in red, and success rate of prediction is shown in blue, which is less, but this always is expected because we are assessing using the data which were not in the classification. The random forest also calculates the importance or predictive power of each variable used in classification by providing raw and normalized values. The variable importance in different experiments were somewhat different, but almost in all of the experiments, PCA, proximity to volcanic intrusions, lithology, chloride, and sericite alteration had the highest importance. Proximity to faults, to northeast trending minor faults had medium, moderate importance, and also we can see that susceptibility shows high importance and resistivity some moderate, and magnetic data reduced to polar upward continuation has some moderate to low importance. In another experiment, we applied the model on a smaller area, which is the area 3, and we used the same variables and the classification again repeated 10 times using different sets of random points. Here we can see the probability map for the smaller area, which is limited with the presence of VMS mines and deposits. The map shows is similar, but there are still some differences in the new map. The overall accuracy, again, when assessed with the training data, is as high as about 90%, and when using n-fold accuracy, we get somewhat lower accuracy compared to the large area. The main difference between these two maps were in variable importance. Except for the PC4, proximity to volcanic intrusions, lithology, and color and sericite, and the other variables showed somewhat different importances, especially chloride, which had a high predictive power in the large area, now gives a moderate importance. And proximity to minor northeast trending faults also has some reduced importance in the new map. The same applies for PC2 and PC6. We can see that they have now lower importance. As a whole, the susceptibility maps have better predictive power in large area, but in the smaller area, we have the resistivity maps show higher importances. This is the first experiment we had, and it shows that variable importance is sensitive to the region of interest. So the study area should be selected properly. And as for summary, the VMS probability maps created in all experiments are similar and show very high performance with respect to VMS, mineralization, and deposits. With respect to the test data, all maps show moderate accuracy. Using imbalance ratio of non-VMS to VMS, in this example 1.5, resulted in lower classification, 0.76 versus 0.78, and prediction accuracies 0.73 versus 0.83 when assessed with the classification maps, but performs better when assessed with the probability map. This map reduces the percentage of area classified as VMS by about 10%. PC4, which accounts for high contribution of lead and gold, proximity to volcanic intrusions, lithology, and alteration maps show high importance in all of the experiments. high importance value of the lithology map complies with the deposit model in Pouran, which considers VMS deposit as being volcanic hosted. The high importance values of proximity to volcanic intrusions agrees with the importance of these intrusions as a heat engine driving the hydrothermal system. High values of chlorite and sericite maps also complies with the association of these alteration zones with VMS deposits. Proximity to northeast trending faults show the moderate importance in most of the experiments. Changing the regional area to a smaller area where the VMS mines and deposits are present results in considerable changes in the importance of variables. The geological constraints on a mineralization type could be the best way to select the ROI. Thank you for your attention. That's it.
Great. Thank you very much, Pouran. We do have time for a question. Please go ahead, Ed.
Yeah, just a quick question. I noticed that you used the cross-validation with random forests. And I guess there's some controversy over whether cross-validation is necessary because random forest has a built-in form of cross-validation. And yet when you did that, you reduced the accuracy of prediction by about 10%. So I'm curious if you have any comment on that.
Yeah, I think this is just being on a safe side to still use the enfold cross-validation. You mean the enfold cross-validation or any cross-validation? Because once we used the training data, that was also cross-validation, and we got a very high accuracy using the cross-validation, even more than those we got from the probability map from area frequency.
Right. Well, I guess what I was looking at was just how you use the enfold cross-validation in your example there. It just seemed to me that if it reduces the accuracy of prediction, how do you explain that in terms of the mechanics of the methodology, or is it a change in the information?
Yeah, actually, to me, getting 98% accuracy was actually a little bit overestimation. So I was thinking that we should try something that shows a little bit the real accuracy, but maybe enfold that cross-validation is also decreased too much. Maybe the accuracy could be something between these two. We can consider that accuracy not as high as 98, but not as low as 70%.
Yeah. Okay. No, that makes sense. That's a really nice study. I think there's lots of things to explore further there. Thank you.
Thank you.
Bruno, you have your hand up. We have time for one more question.
Okay. Thank you. Nice talk, Pouran. You found the northeast trending faults were more prospective. Did you also have the east-west trending fault, and was the prospectivity map found by itself that the northeast trending faults were more prospective for base metal mineralization?
Pardon me, would you please repeat? I just wanted to bring the I just want to show again the you can see that most of the deposit mines and deposit VMS ore bodies, yet here they show some association with the northeast, but with the northwest there is not much associated with these ones. Especially we can see in the minor ones, we see higher association of the VMS deposit with this group of the parts.
Okay. So you okay. So you look at where the occurrences of base metal and the orientation of the fault. Okay.
Yeah, this was based on the VMS, actually the mineral deposit model we created at first, that which criteria could be important in
Okay,
in the
no,
model.
and the reason I was asking is because over there, the northeast trending fault tend to be synvolcanic fault, whereas the east-west one or the one associated with gold mineralization with the orogenic gold mineralization. So I was wondering if that was something that the prospectivity model found, or that was one of the starting, let's say, starting data for the model.
Yeah, we selected these two trends because we wanted to know which one shows a better predictive power, which one is associated with that. And we, by just looking at this, we could see that these minor northeast trendings should have high predictive power, high values. And this was shown in the values which in the results we got from the model. But we actually, in another method which I explained for the for the larger area, we didn't use the 3D geophysical data. And for that, I can show the this one. Here in this model, we didn't include the 3D geophysical data. So here we can see the again minor northeast trending, which has high predictive value, and also the major ones show some moderate importance. And in the previous model, this was not very high, but in the absence of the 3D geophysical data, here we can see these two groups still show higher values, but northwest trending faults in both model show to have lower importance.
Okay, thank you.